This video accompanies learning IoT with Python and Raspberry Pi. In this lesson, you will learn how to write recursive functions. Recursive functions are functions which call themselves. An algorithm, when implemented using a recursive function, has the following characteristics. The function continues to call itself until the stopping criterion is met. Once the stopping criterion is met, the function returns a value rather than calling itself again. There is a known value for when that stopping criterion is met. Go to Programming and select the Thani editor. And let's create a new script. In this script, we'll write a short recursive function, which will allow us to see the order in which function calls and returns are made when we write a recursive function. The up-down function takes an integer parameter, n. The function prints out the value of n before and after the conditional statement. The function has a stopping criterion when n is equal to 5. We'll thus add a conditional statement that as long as n is less than 5, we'll call the up-down function again, passing in an argument of n plus 1. The function continues to call itself, incrementing the value of n by 1 at each function call. Let's next create a main function that calls the up-down function and passes in a value of 1 for the argument. And then we'll call the main function. When a function is called, an activation record is created that holds the execution context of the function during a function call. This block of memory is allocated at the top of the process stack and includes the return address, parameters, and local variables. Each function call creates a new activation record. The activation record is removed from the stack when the function returns. The last called function is the first to return when functions call other functions. In the case of recursive functions, the last call of the function is when the stopping criterion is met. This function call will return first, then each of the other function calls will return. In this case, the first function to return is the function where n was equal to 5, the value of the stopping criterion. Let's look at how to compute the numbers in Fibonacci series using a recursive function. Leonardo Fibonacci of Pisa was a medieval thinker who created Fibonacci numbers. And Fibonacci numbers have a relationship to both botany and classical art. The first number in Fibonacci series, f0, is equal to 1. The second number, f1, is equal to 1 as well. The value of each number in the Fibonacci series is the sum of the previous value and the value before the previous value. The numbers in the series are thus 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. If you wanted to compute the value of f5, you would compute the value of f2, which was equal to f1 plus f0. That's 1 plus 1, that's equal to 2. f3 is equal to f2 plus f1. That's 2 plus 1, that's 3. If we want to compute f4, that's f3 plus f2, and that's 3 plus 2, that's equal to 5. And f5 is equal to f4 plus f3, and that's 5 plus 3, and that's equal to 8. So we want to write a script that uses a recursive function to calculate a number in the Fibonacci series. The recursive function f can be written since there is a stopping criterion of n is equal to 1 or n is equal to 0, and there are known values for f1 and f0, they're both 1, and then the value of fn can be computed as the sum of fn minus 1 plus fn minus 2. Let's say we wish to compute the value of the sixth number in Fibonacci series. So we'll call the function with an argument of 5. We'll then call the function with an argument of 4, 3, 2, 1, 0, 1. Then we'll call the function with an argument of 2, 1, 0. Then we'll call the function with an argument of 3, an argument of 2, an argument of 1, an argument of 0, and then we'll call the function with an argument of 1. Notice that we continue to call the function until we reach the stopping criterion of either n is equal to 1 or n is equal to 0. Once we return from both of those function calls, we can return from the function call where the argument was 2. Then we call the function where the argument was 1, and we return a value of 1. Then we can return from the function call where the argument was 3. And then finally, because we already had computed the value when the argument was 4, we can finally return from the function call when the argument was 5. Let's create a new script called Fibonacci Numbers. We'll create our function, f, and pass in a single parameter, n. We'll add in the stopping criterion. If n is equal to 0 or n is equal to 1, we're going to return a value of 1. Otherwise, we'll return by calling the function f, passing in an argument of n minus 1, and we'll call the function f, passing in an argument of n minus 2. Let's create a main function that will call the function f and pass in an argument of 5 and store the return value in result. And let's print out the value of result. And we'll call the main function. And then I'll save this script. And then let's run this script. Let's next create a for loop. Since we wish to compute a number of the values in Fibonacci series, and in this case, our I will go from 0 to 19. Let's print out the value of I and the value returned for each function call. Let's run this script. I previously mentioned that Fibonacci numbers have a relationship to botany. There are sets of clockwise and counterclockwise spirals found in the florets in the core of daisy blossoms. There are 21 clockwise and 34 counterclockwise spirals. These are two adjacent numbers in the Fibonacci series. The spirals in a pine cone have a ratio of 5 to 8. The bumps on a pineapple have a ratio of 8 to 13. You can see that these are also adjacent numbers in the Fibonacci series. Let's next compute the ratio of adjacent numbers in the Fibonacci series. So we're going to set the previous value equal to 1, since we're starting at the value of I is equal to 0. And then we'll compute the ratio of the current value, result, to the previous value. And we'll print the value of the ratio. The reason that I want to compute the ratio is because the ratio of adjacent numbers in the Fibonacci series goes to 1.618 as the value of I increases. This value is the golden ratio found in classical art. and then we'll set the new previous value equal to the current value. Let's run this script. Let's display the ratio with 6 decimal places of precision rather than just 2 decimal places of precision, so that we can see that the ratio is approximately 1.618. The facade of the Parthenon in Greece fits inside a golden rectangle, which is one of the places that the golden ratio occurs. In order to see a golden rectangle, take a square that's in black, divide it in half, the red line, add a circle of radius equal to the bottom dividing line to the top right-hand corner of the square, and then extend the rectangle to include the circle. There are other places where the golden ratio occurs, such as in decagons and pentagons.
Go to www.learningiot.net for more information on where you can buy Learning IoT with Python and Raspberry Pi.